Okay, it's recording.
Okay, so we're broadcasting into interstellar space now. Welcome everybody to Dr. Hugh Ross's Paradox class. This morning without Hugh Ross. He is doing another Zoom seminar to another church this morning, and we have the distinct honor of having a guest. Her name is Karina Malko. She's an observational astronomer, and she's going to be talking, I think, about planetary formation, but I'm going to let her introduce herself. So, Karina, could you tell us a little bit about your background and where you're working at and where you live, and maybe even most important, how did you come to faith in Jesus Christ?
Yeah, sure. So, hi, everyone. Thank you for this opportunity of being here and be able to talk a little bit about what I do. So, I'm an astrophysics. I just finished my PhD 2 years ago. So now I'm currently working in Chile, in Valparaíso. So it's my first postdoctoral position. And as Mark said, I work in planetary science. So I basically study stellar and planet formation. So in contrast with what Dr. Ross was teaching us these last couple of classes, I work also in planetary systems, but when they are very young, when they are forming planets. So I'm an observational astronomer. So I actually go to the observatories, to the telescope, and take data of the stars, so we can study how these planets form. I did my PhD in Mexico, and now I'm currently living in Chile because of this postdoctoral position. And about my faith, well, I have the great honor of born in a Christian family. So I am a Christian since I was a little kid, and I always have a strong faith in God as a creator of the universe, of everything. So that has been a real blessing. And I believe also in Jesus Christ as my Lord and Savior. So once I enroll in this scientific career, because I always been passionate about stars, about the universe, so that always have caught my attention. I start having these contradicted thoughts of, well, I think the Bible tells me this, but science tells me this other scenario. So I wasn't at the first, especially at the first years of my PhD, I wasn't getting these complementary visions of what the Bible says and what the science says. So it was, in the beginning, was a little bit frustrated because I thought that if I believed in all this scientific evidence, I was somehow deceiving God, because God does not what the Bible said, because I grew up thinking that the Bible teach John creation. So was when I found the Reasons to Believe website and the teachings of Dr. Ross, that I finally was able to put all these things together, and was a really turning point, and was such a blessing and inspire. So now I can be both scientist and Christian, and now I'm very much motivated in pursuing this science and learning more about this scientific evidence that makes a stronger case for the creator. So that has been such a blessing, and I'm very grateful for all the work that Reasons to Believe have done over the years.
Thank you, Karina. If you want to go ahead and start your talk now, that would be great.
Yeah, sure. So let me share a screen here. You can see my screen now?
Yes.
Okay, you can see the mouse, the cursor?
Yes.
Also?
Yes.
Okay, perfect. So, well, I'm very glad that I can have this opportunity of talking a little bit of what I do. So as I said, I will talk about the evolution of planetary systems and protoplanetary disks around young stars. So I basically gonna focus my study on low mass stars, so stars like our sun, but when they are really, really young. So why do we care about these protoplanetary disk systems. So we've been talking about the solar system, and we know that we have this beautiful design and configurations of our own solar system with giant planets, with rocky planets, with these beautiful asteroid belts. But if we can go back in time and ask what the solar system looks like when it was really young, when it was still growing and forming. So as you may think, the solar system will look like something like this. So we have the protosun at the center, and it's going to be surrounded about this material, about these disks, then disks of gas and dust. So our job is to try to figure out how from this we get a solar system and a planetary system that like the one we have. So our job is to try to disentangle this puzzle of what are the physical properties and the physical mechanisms that are acting on this protoplanetary disk where we believe planets are formed. So that is why it's very important to study protoplanetary disks, and that's what I do. So we cannot talk about protoplanetary disks without talking about stellar formation. So as you may think, stars form from the collapse of these dense clouds of gas and dust, because these clouds always have some degree of rotation. Then by angular conservation momentum, this natural collapsing event will produce disks around a star. So just by forming stars, you're naturally gonna have a disks around a star. So these systems will evolve in time, because what it happens is that at earliest stages of a star formation, you wanna have this huge chip of gas and dust, and that material from that envelope will fall into the disk. So here we fall into the disk through the star. So basically, the disk is the one that is feeding material through the star, and that way the star can grow. So the way that this material goes from the disk to the star is through these accretion floats, what we call accretion floats, that are going to be dependent of the magnetic properties of the star, the magnetic fields of the stars. So over time, this material from the envelope run out of material because material is getting into the disk through the star. And in early stages, the stars are really active. So they have these huge stellar winds and jets that also dissipates material. And then you start getting grain growth on the disk. So you are getting larger and larger solids until you end up with a planetary system, like our own planet, solar system. So you have the star, you have the planets, but you have barely no more gas. So the formation of this is tightly related with the formation of the stars. So now how can we study these disks? So first, we need to know where to find them, how to observe them. So for how long these disks lived. So over the years, astronomers have observed different stellar populations with different ages. So if you go to the very young star forming regions like Taurus and Lupus, just 1 to 3 million years old, so very young, you see that approximately 90% of the stars in those regions have disks. So if you have 100 stars, 90 of them will have disks around them. If you go to more evolved systems, so middle age, what we call middle age disks, from 3 to 5 million year old, like Sigma Ori in Orion, this here in these regions, only 20% of the stars will have disks. So 80% of these stars would already have dissipated their disks, have evolved. So if you go even to more evolved systems, so up to 10 million years, now you barely have stars with disks. So only very few tiny fraction of stars have disks. So now astronomers have come to realize that disks, protoplanetary disks, only live up to 10 million years. So when we planetary scientists in the early phases talks about all systems, we are referring to about 10 million years. So that is good to have in mind. So everything that happened on this planet formation have to happen within this time scale of 10 million years. So how do we study these disks? Well, over the years, we have these amazing instruments that can give us a hint of what is going on in the systems, but one of the hallmark of observations has been ALMA. So ALMA is an interferometer that observes at 2-millimeter wavelengths, is an array of antennas that have an amazing properties and has been a revolution in this field. So these pictures that I show you here is actually before ALMA. So you can compare. So these are several sources that we believe have disks. So you see that all we have is this blur, bright clump of material, but we cannot really see detail on it. So this is before ALMA. You can see the years here. So 2011, 2001, that's all we have. So now with ALMA, you get this. So you have amazing pictures now of these protoplanetary disks, of these systems. We can actually see very detailed observations of this, of what's going on in the system. So you see these amazing designs, amazing structures. For example, this one is a very famous picture. It's HL Tau, because it was the first image observed at this resolution. And I just remember my tutor sending me an email, like, have you seen this picture? And yes, of course, it was amazing, because it now gives us the possibility of study these systems to such a detail. So this is very young, it's just 1 million years, and you can see that it has all these rings, all these gaps, dark gaps in there. So now we can have an idea of what's going on. We have different flavors. So you have some of them that are like normal distributions, others have these beautiful spiral arms. So now we are in that stage that we can, okay, we observe this now how can we explain that? That's what's revolutionizing in this field. So what are these disks? What these disks are made of? So protoplanetary disks, as you can see here, are composed of two main components, gas and dust. So the gas on these disks is basically the dominant, is what it composes the bulk of the mass of the disk, is 90%. But even though dust is just 1%, it actually plays a key role in the evolution of these systems. Why? Because dust dominate the opacity of these systems. The opacity is just the ability of the material to absorb stellar light. So basically it dominates the thermal and geometrical structure of these disks. So because these disks are really bright, the dust in these disks are really bright at certain frequencies, now they've been a key diagnostic tool to detect these disks and to characterize these disks. Also, dust plays a huge important role in this chemistry, because the formation of molecules actually happens on the surfaces of these grains. And of course, you need dust in order to form planets, because these are the building blocks of planetesimal formation. So my study is based on the dust component on the protoplanetary disks. So you can see here that we're gonna have these two regions of the disk, the upper layers of the disk that are composed of a small dust, and also the midplane of the disk, which is composed of bigger grains. So the main heating mechanisms on these systems is, as you may think, the radiation from the central star. So the star is heating with radiation the surface of the disk, so the upper layers of the disk, which are composed of a small dust. And this small dust is very efficient at absorbing stellar light and re-emit it at longer wavelengths. So the upper layers of these disks are going to be hotter than the midplane, the more dense, cold midplane. So that will give us a very useful tool when we want to observe these systems. So here I show you the electromagnetic spectrum. And as you can see, humans, here is the optical region of that spectrum. So these are the colors that we human actually can see. But we're going to be talking a lot about this other region from the left of this image. So we're going to be talking about the infrared and the sub-millimeter ranges. Why? Because as I told you, what we are looking is dust that is being heated by the star. And as we know, heated sources emit at these wavelengths, so infrared and sub-millimeter. So we're going to be using data sets of two main instruments, which are ALMA, that I told you was an array of antennas in Chile, an interferometer that observe at sub-millimeter wavelengths, and also BLT in Paranal, which is also in Chile, and it observes at infrared wavelength. So a very straightforward rule in astronomy is that if you observe something at, for example, sub-millimeter, so 1 to 2 millimeters, the emitting particles is going to be around that size. So we're gonna be just looking at these two different range of sizes of dust in this disk. So the millimeter, 1, 2 millimeter, and the infrared, that is very smaller grains at micron sizes. So going a little bit further on this structure, here I show you a sketch of what a protoplanetary disk would look like. Here, the gray area is the gas distribution of the disk, and you can see that it's not homogeneous. So you're gonna have denser parts in the inner regions, so close to the star, and through the midplane is going to be more gas than in the upside. So that will produce a gas pressure gradient, and that is going to produce a very interesting process on protoplanetary disks. And it goes like this. A small dust that is going to be in the outer parts of the disk will settle to the midplane. So we're gonna have this vertical settling of dust, where dust going from the upper layers of the disk to the midplane will start growing, but also is going to move in the radial direction. So that's what we call the radial drift of the material. As I mentioned, disks, the material from the disk go from the outside to the star. So in the way in through the star, dust particles are also going to start growing and growing. So that's what we call the radial drift. So the midplane will be colder and will emit in millimeter to millimeter. So we're going to observe that with ALMA. And the infrared will be proving or tracing just the small dust that is at the surface of this of the disks. That will give us clues of what is going on at different heights of the disks. So one issue that we astronomers have come to challenge all these processes is the radial drift dilemma. And it's because it does go from the outside to the inside. So what is stopping the grains? So we need the mechanisms that actually can stop the grains from going into the star, because we know that planets exist. We have this beautiful planetary system, so there have to be some mechanisms that stop the grains. So that's when all these observations have been of huge improvement on our knowledge on these systems. Why is it important to observe these disks at different frequencies or at different wavelengths? Well, here I show you a very good example. This is it's a solar analog, so it's very important source. It's TW Hydra. It's 10 million years old, but it's very sun-like star. So if you observe it in the infrared, so the scattered light, which is just light that is being reflected from this small dust at the surface, you can see that it has this beautiful configuration, beautiful design of bright greens, dark gaps. But if you observe it with ALMA, so in the submillimeter, larger grains, you see that the disk is more compact, more small. We're tracing the inner parts of the disk, and you can also see some structures there, but it's very different, one observation from the other. If you also go and observe emission lines, so gas tracers, you can see that it has very different behaviors. So we need to have these multi-wavelength observations in order to have a wider picture of what is going on in these systems and be able to explain what physical mechanisms can explain these things. So this is actually a source that I've been working on right now. So I'm currently working in these disks. It's a John disk in the constellation of Lupus. And you can see here that in ALMA, so 2 millimeter grains, you have this beautiful ring of dust and a central cavity. So you have a central cavity with no dust, and you have this beautiful ring around it. Actually, is the low mass star with the biggest or the largest cavity observed in the submillimeter so far. So if you now observe it in the infrared, so you are observing a small dust, which in this case, in this central panel, is this color emission. You can see that the contours here, the white contours, is following this ring of the left. So these are large grains, and you can see the small grains are inside this cavity. So that is also giving us a clue of what may be happening in this system. We have larger grains a little bit out, and we have smaller grains from the surface a little bit in this cavity. So that can give us a clue of what's going on. For example, if you want to explain this type of configuration with planets, you need low mass planets. You don't need giant planets. And we're gonna see that a little bit later on. So having these multiple observations at different wavelengths can give us a clue of what is going on. Something very peculiar about this source is that if you go and observe the gas composition, the gas component, so here again is the ring of large grains in contours, in white contours, and in this case, the gas emission is in color. So you can see that the gas is all over the place. So it's very way into the cavity, very close to the star, and really far away from the dust. So that is also something that we need to explain with models. And that's why these very high resolution observations are crucial in order to understand what is going on. So now there's been a lot of effort in trying to find more and more disks and try to observe it at these high resolution observations. So here I show you an amazing job that is just been done 2 years ago. So you see that this is a really new field of study. It's called a D-sharp sample. You have 20 disks and observed with ALMA. So we are tracing the mid-plane of these sources. And you can see that we have different beautiful configurations, beautiful designs. You have sources like these ones on the bottom right, where you have these beautiful rings, very, very narrow rings. You have other sources that are basically small with no much structures there. We have spiral arms. We have some structures that are not symmetric in the right direction, in the simultaneous direction. So we have all these type of different superstructures that are happening really early on in the system. So if you see the mean age of this sample is just 1 million years. So apparently, very early on in the systems, you already have these superstructures. So first, we believe that these type of rings and spiral arms are the result of planets already formed in the disks. So if this is the case, then planet formation have to happen very, very fast and very quickly in these systems. So alternative positions have been invoked in order to explain these superstructures at such young age. And these superstructures are essential ingredients for reconciling this drift paradigm, this drift dilemma that we have in planet formation. So it seems that very early, you have already this discontinuity on the distribution of gas. So you don't have this monotonically decreasing distribution of gas, but you have these superstructures that can trap dust and actually promote the planet formation. So that is with ALMA in the submillimeter. And now we have also found these superstructures in the near infrared. So again, this is small dust close to the surface of the disk. And we can also find these beautiful rings, gaps. We have huge and massive disks. We have others that are very faint and small. So we are actually also finding these superstructures at the upper layers of the disks. So that gives us an idea of what's going on in this system. So now there's a lot of capabilities and improvement in instrumentations that we can actually see this detail, this level of detail. So astronomers have, we love to put things in groups and classify them. So we now start classifying these samples of disks. So we have like ring systems, spirals, faint and small ones. And what we want to do is try to observe more and more of these sources and see if one of these morphologies follows some empirical trends with other parameters, like stellar parameters. Is it something because of the star? Is it something because of the environment where these sources are? So we can have an idea of what is going on. Is it because of the age of the region or not? Right now, we are not completely sure of what is producing this type of superstructure, but it's really an exciting moment to study planet formation, actually. So this is a very radical example of this situation. For example, this is a Herbie star. So it's a star that is a little bit more massive than our sun. It's 1.7 times more massive than our sun. And you can see that if you observe a small grain, so the surface of the disk, you see these beautiful spiral arms that we can now actually observe with detail. So it's beautiful. But if you observe it in the mid-plane, so denser, colder parts of the disk, you just find a ring of dust and a central cavity. So that tells you that there are different processes happening at different heights of the disks. And that's something that models, theoretical models, have to account for. And now that we have all this evidence of superstructures, we are now in the time of trying to explain this physical mechanism. So what is really going on here? What is producing all these features? So basically there are two main propositions. One, of course, it's our favorite ones, planets, and the other ones are not, they're not neat planets, but they are based on gravitational instabilities in the disk. So basically they are saying that you don't have this monotonically well-distributed gas density at the beginning of a system, but you have this inhomogeneous distribution because, you know, gas and material is getting into the disk, accreting into the star. So because you have rotation, you have different parts that are going to accumulate more gas. So dust is going to go there and going to produce all these superstructures. And the good thing about these two methods is that in the case of no planets, you can actually form these superstructures a lot more faster than planets. Because planets, one of the problems of planets is that it seems to take too long to be able to form these superstructures. So here I got three main superstructures that we observe, as I showed you before. So we have the central cavity and the ring. You have this configuration of multiple rings and gaps, and you have spiral arms. So how we explain this? So for the first case, so the cavity, the central cavity and the dust ring, you can explain it with giant planets. So you need to have multiple giant planets actually. But the giant planet is massive enough so it can carve, it can create a wire enough cavity. So if you have multiple, the overlapping gaps are going to clear a central cavity. So that cavity, usually if are giant planets, is going to be in the dust and in the gas also. But it can also be explained by a mass loss in winds. So as you may know, stars are not static, so they're active, they have this high radiation energy, and later on under evolution, they have this massive high energy radiation that simply clear out the inner parts of the disk and create also this central cavity. In the case of the rings and gaps, multiple rings and gaps, you can also explain it with planets, but in this case, you need low mass planets because low mass planets are not that massive. They can still accrete some material, but they only create narrow gaps. So you can actually have this configuration with low mass planets. So that gives us a clue of what type of planetary system is forming. Of course, before we have the naive idea that we need one planet for each single gap. But now there's a lot of papers that have shown that you don't need that much planets. You can have a low mass planet and it can produce these resonant motions that can configure the dust this way. Now the additional scenario with no planets for this case of ring and gaps is based on these turbulent motions that can have this configuration because of magnetic fields, instabilities on the disk, and can also produce this. So we're actually not sure what is the reason of this. So there are two main visions. There are two types of astronomers. Ones that believe that we're actually seeing protoplanetary disks, so disks that are actually forming planets and producing these superstructures, or planet hosting disks. So actually disks that already form planets, and what we are looking is the interaction of these planets already with the disks. So these are the main two positions right now. But of course, as everything in nature, it can be the combination of several mechanisms acting at once. So for example, in the case of spiral arms, you can have massive planets that produce these resonance motions, and that can produce a gravitational collapse of these denser parts in the disk, and can also produce these spiral features on the disks. So another possibility, an alternative scenario that is gaining momentum right now is also in the line of no planets, and it has to be with snow lines. So as you can imagine, the disk, as I told you, in the inner parts of the disk, the star is really close, so it's very hot. So the outer parts are going to be colder. So basically the snow line is where the volatiles, outside the snow line, the volatiles the temperatures are low enough so these volatiles can freeze in the surface of the dust. So when the dust start migrating inward and pass through the snow line, now that volatile became gas, so it condensate, and you can maybe think about this, that it changed the dynamics and the movement of the dust. So that have also been proposed to explain some accumulations, some accumulation of dust in these rim and gap systems. So for example, for the image of Echeltau, the one that I told you that it was the first image of ALMA for this source, has been proposed this snowline scenario where volatiles of different species, for example, hydrogen or CO, these gaps seem to be correlated with the position of these snow lines on the disks. So that are basically the main physical mechanisms that we astronomers have proposed in order to explain these superstructures. So now, as I told you, it's a very exciting moment to study planet formation. We now have the capability of actually looking at planets. So as you know, since yesterday, there have been 4,197 confirmed exoplanets. So there's a lot of exoplanets over there, but most of these exoplanets have been confirmed by indirect methods. So by radial velocity, by transients, but actually taking a picture of a planet was very difficult. And it wasn't until a couple of years ago that we have the capability of actually taking an image of a planet. So here I show you an image of an exoplanet that I usually love, and it's very also famous. It's a star, a low mass star called PDS 70. And you can see here, this is taken with Paranal. So in the infrared, we are looking at small grains in the surface of a disk. And you can see that have this green configuration and a cavity. So this part over here is the cavity of the disk, and you can see this bright blob here. So this was observed 2 years ago, and it was now being confirmed as a planet. So it's actually bound to the system. And if you look in the right side of the picture, you can see also the overlap of the ALMA observations. So you can actually see the ring of larger grains. So we have a central cavity and a ring around it. And now we even have confirmed a second planet on the system. So it is PDS 70C. So we are now actually getting into the point that we can actually observe planet in information. So the good thing about these two sources is that now they have also been observed in gas, so in line tracers like H-alpha, which are indicative of accretion. So actually these sources are bound to the system and actually accreting material from the around it. So that means that this is actually a planet information. So again, this method is biased, so we can only observe this type of planets that are really massive, so are giant planets. If you see here, and we compare it to our solar system, you can see that the orbits of these two planets are more or less from Uranus farther away. So it's not closer in, but they are giant planets. So they have masses of less than nine times the mass of Jupiter. So it's very exciting, and astronomers more and more want to have these very high resolution observations. And now what we hope is that we can do actually larger populations of this, so we can explain and we have a better picture of how planets form. So basically here I want to show you a short video of what is the classical view of how planets form. So here I will go and put it. I hope you can see it. Put that. So you have the star, the material is going around the star. They start forming larger and larger grains, and you start forming these bodies, these planetesimals that in the way orbiting the star start cleaning their materials around them and start growing, accreting material, and they are consuming the gas and the dust until they are actually consume all the gas material, and you end up having a planetary system like our own solar system. So you just have the star and the planets around them. So that is basically the main idea that we have about how planets form. So now the takeaway message that I want you to take about this talk is that, well, these are very important. They are tightly related to stellar formation, to planet formation. These are these that are composed of gas and dust. Even though dust is just a tiny fraction, it actually plays a huge role in forming in setting the properties of the distribution, the thermal and geometrical distribution of the disks, and are the building blocks of planets. So that's why we studied dust. This evolved over time, forming larger bodies. Of course, in order to do that, we need to have some dust getting trapped in these pressure bumps. So for that, we need to have these superstructures that we now are capable of observing. So the gas will have these inhomogeneities, dust will get trapped into that, but the origins of these superstructures are not yet clear. So there are two main propositions: planets. So we're actually looking at planet hosting this that are affecting what we see, or actually based on instabilities on the disk. So the disks have these many multiple physical processes happening. So you have these inhomogeneities in the gas, how the gas and the dust interact between each other also plays a very important role. And you can have these superstructures very early on without the needs of planets. And then from those superstructures, then you will have planets. So we are in these two-side views that if we have protoplanetary disks or planet hosting disks. And planet formation in general, or planetesimal formation at least, is a quick process. So before we have this thought that planets takes, I don't know, 500-600 million years to form. Now we know that that's not the case. Planets have to form very early on in the system. So this is why this huge amount of data and new observations and models are actually playing a huge role in improving our knowledge of how we form this amazing solar system that we have. So all this just talks very loudly about this amazing creator that we have, that have made everything possible, that control everything, and then have give us this amazing planet where everything seems to be just right, just in the right place at the right time to life to come and can emerge in this planet. So thank you, and I leave you with these beautiful birds that I love. The heavens declare the glory, and the sky proclaims the word of his hand. So thank you very much.
Marina, what an amazingly good talk. Thank you so much. And those visuals were terrific. I bet you didn't put that together just in the week you had to know that you were going to join. If you did, you probably got no sleep. That was really wonderful.
Yeah.
Thank you so much. Are you ready for some questions?
Yeah, sure. Should I stop my chair or my chair screen?
Probably, yes.
Okay, sure.
Okay, very good. So Stephen in Spring, Texas has a two-part question. He says, when planets get kicked out of star systems, where do they go? And do we have any idea what the average number of ejected planets per star system are?
Yeah. Yeah, there's a lot of models that predicts that in a planetary system, you will have several rocky planets that, or giant planets even, that with the interaction of stellar companions or even the same planets will get kicked out of the system. So where do I go? They just get out of the planetary system and start orbiting or moving in the stellar cluster that the planetary system is. So that's where they found it. In the last couple of years, now we are able to actually observe this planetary in isolation. So we call it the isolated planetary mass companions. So we are being able to detect around, I think, if I'm not mistaken, about like 90 of them now. Of course, it's very difficult to observe it because they are really small. They are not that bright. but we don't have actually an idea or a robust idea of how many of these will exist, but we know that it should be a lot. So there are a lot of planets, isolated planets around planetary system. So there, the thing is being able to catch them, to observe them. But yeah, they start moving in the stellar cluster that the planetary system performs.
Thank you. Steve Rockstad here in the Los Angeles area is asking, how similar is a protoplanetary disk to the rings we observe around planets like Saturn? Are they formed with similar processes?
Sorry, I didn't get the question. You were like...
Okay.
Can you repeat it, please?
Sure. How similar is a protoplanetary disk to the rings we see around planets like Saturn? Are they formed, Are they formed with similar processes?
Yeah, well, that's another very wide field that right now is being growing, because we now have, well, we're not there yet, but we're going to have the capability of actually observe disks around planets. So right now, what we think is that there are two main propositions, that they are a scaled down version, basically, of the protoplanetary disk. So what the planet is forming, because it's rotating, it will produce this disk around the planet. And we can actually observe these planets that, because of the flux that they emit, their sizes is just too huge, too large. So that we understand it as the planet is actually have this disk around it. So that is one proposition that is just same as the stars, as protoplanetary disk. But there's another propositions that are also being invoked to explain this disk around planets that have more to be with maybe instabilities, gravitational instabilities that are produced because of the interaction of the planet with the gas and the dust, and that can also produce these stable orbits around the planet, but we are not entirely sure. So we need more observations, high resolution observations, to actually have a better idea.
Thank you. Doug McComb here, and also in the Los Angeles area, asks a couple of different questions. I'm going to ask the first one first, and then the second one a little later. I'm going to say, he says, good morning. Thank you so much for being here with us. May I ask you, how did asteroids form? Did any of them result from the collision event that formed the Earth's moon?
Yeah, asteroid formation, I mean, the basic idea that we have is that the result of the leftover evolution of the protoplanetary disk. So once you have dissipated all the gas, you have formed these massive planets, rocky planets, giant planets, then because of collisions, as he says, because of collisions of these planetesimals, or maybe kilometer size dust or bodies, as you can see, if you don't have gas, then these dust can move a lot faster, and they can produce these cascade collisions, and then those material will be around the disks and will form these asteroid belts. So yeah, asteroid belts form as natural, maybe byproduct. Of course, you need certain characteristic and conditions to form it, but it's just a result of this interaction with those particles that are collision and hitting each other. So yeah, it's like the trash that it lets over after planets form. Yeah.
Thank you. Another question from Steve Rockstad. He says, how far away are the protoplanetary disks that you showed us? Can you resolve them with a single optical telescope, or do you need to use an optical or radio interferometer?
Yeah, thank you for that question. Yeah, I forgot to mention that the protoplanetary disk, the average size of these systems is about 100 AU. So, you know, 1 AU is the distance from the sun to the earth. So these are really, really, really huge structures, and that only in the dust, in the gas, can be even larger. So even though in the scale of a protoplanet of the solar system is huge, but actually you cannot resolve it with a single telescope. First, because as I mentioned, what you see here is the emission from dust being heated. So it's actually emit in the infrared and in the submillimeter. So with optical telescope, you're not gonna see that. You're only gonna see the star. But these are really tiny features, if you wish, that you cannot resolve it just with a single telescope. That's why you need these huge telescopes, interferometers, or really big telescope. The one that I show you in Paranal is 8-meter diameter telescope. So you need huge telescope in order to see that little scales of the star and the disks. So yeah. I think you're mute. Oh, yeah.
Yeah, there we go. Jack Zaleski says, I have read that double star systems are quite common. How does the presence of a second star affect solar system creation? Does each star have its own planets, or does a single solar system form around the picture for presenting?
Yeah, that's a great question. Yes, definitely. Binary stars have come to, we have come to realize that binary stars are really, really common. Actually, I think half of the stars are in binary systems. So even binary, 2 stars or multiple. So in this case, for example, you need to have additional observations that are tackling just the central star. So you can actually resolve if the star is just a single star or a binary star. So in many of these sources that I show you, we don't actually know if the star is a binary or not. For example, in the case that I'm currently working, so this huge cavity that I show you is actually being proposed that the best scenario maybe it is a stellar companion. So you have binary system because you have a star instead of a planet there. So it's more massive. So it can create this huge cavity in the dust. So we have seen everything. So we have seen binary system and this around it. We also seen binary that are really farther away from each other. So both have disks. And now we are actually looking at multiple systems. So there's this one very famous system of a binary system here at the center. Then you have a disks, and then you have another multiple system outside the disks. So now it's all these incredible observations that we are now trying to explain how that can be stable, how can that dust create in this type of system. So really there is everything, every possible scenario maybe you can find. But actually, in order to have planets and don't have these very turbulent motions and resonance that are going to destroy your disks, binary have to be closed or really wide away. So you cannot just have a disk in one single star.
Thank you. The second half of Doug's question, he says, do the rings of Jupiter, Saturn, and other planets consist of only ice, or are there other materials that they consist of?
Mm-hmm. Well, yeah, what I'm aware of is that, yeah, basically most of them are composed of ice, but I don't really know if they have another additional components really. So honestly, I'm not an expert in asteroid belts or disks around our giant planets, but mostly yes, they should be ice, but I'm not sure. So maybe Hugh can give us a hint about that next week. You are still mute, I think. Sorry.
Boy, I'm just not used to turning this on and off. One question, which is a bit of a technical question. Could you make the presentation available for us to download, the PowerPoint?
Yeah, sure.
Okay, great. I will
make it ability for you, yeah.
Okay, thank you. Steve Rogstad again says, I work for the NASA Deep Space Network at the Jet Propulsion Laboratory. I wonder if you have used any of the DSN 34 and 70 meter radio telescopes in your research, or worked with any of my astronomer associates, Joe Lazio, Jorge Pineda, Walid Mahid, Chuck Nudet, or Andrew Romero Wolf, or Peter Gorham.
Yeah, no, I unfortunately haven't used any of those facilities. And some of those names sounds familiar, but I haven't had the pleasure of working with them directly. But hey, you can tell me and we can do something, you know.
Great, thank you. Brian is in League City. I think that's in Texas. How much of a protoplanetary disk never gets incorporated into planet making, and what happens to it? Number two, is there any type of material that as a rule never gets incorporated?
The last part of that question, I didn't quite hear it.
Sure, I'll read them both again. How much of a planetary disk never gets incorporated into planet making, and what to it? And then number two is related. Is there a type of material that as a rule never gets incorporated?
Okay. Well, yeah, that's a very good question. It's have to be with the efficiency of making planets. So we know that most of the mass and most of the material in the disk is actually dissipated because of these stellar winds, or it doesn't get into the planet, but into the star, which is the main gravitational potential that is affecting the system. So a lot of gas and a lot of small dust is going to be in the star. So the planets, the planets form from these protoplanetary systems. How much material do they use for that? I don't have a number, but I guess is a lot less than the bulk mass of a system. And now that is not such a easy question, because one thing that is hard for us right now to estimate is the mass of the disk actually. So as I told you, the dust is just very tiny fraction. So if you want to look at the gas, it's not that simple, because the most abundant molecule in this protoplanetary disk is molecular hydrogen. But unfortunately, this molecule is invisible to us. What we observe as a gas tracer is emission lines, which are in these rotational vibration transitions that we can observe. And hydrogen, H2, it doesn't have a permanent dipole moment, so we cannot observe it. So we have to go with more rare tracers of gas, and we have to make assumptions about, well, if I observe this abundance of CO, for example, how much hydrogen is. So we have to make several assumptions, so it's model dependent. And we also have the complication that we don't know if we actually observing a line that is what we call optically thin, so it can actually go deeper in the disk. So sometimes you just observe a line and you actually observing just the surface of the disk. So the estimation of your mass based on those observations is going to be an underestimation of the mass. So it's not an easy thing to do, estimating the mass of the disk. There's an open debate of how to do that. So basically, in order to resolve that, what we do is try to observe different isotopologues of the CO. So we can trace different heights of the disks, at least in our simple understanding of where these emitting lines are producing, and try to figure it out and have a more robust estimate of the mass of the disks. But that's still an open issue in astronomy, very important one, because it's, essential in order to understand the formation of planets. But yeah, planet formation is efficient, but most of the mass of the disk will be dissipated.
Thank you. Mark Durham from Los Angeles area says that the Earth is extremely rich in uranium and thorium, far more than is expected. What caused this? Was it due to the collider event with planet Theia, or was it due to the Earth being in the just right orbital distance to accrete these elements?
Yeah, that's a very good question. I think Dr. Ross have also talked a little bit about this in previous talks. But what I found, and it was amazing, what I found preparing for this talk, I was reading a review on the solar system birth environment. And they always, you can see in the text sentence like, well, there's a problem with this model because the sun have to be in just the right place, in just the right time. It's just not possible. It just needs so much fine tune. So yes, Earth and these heavier elements that Earth has doesn't have quite an easy explanation so far. So one, there are two possibilities. So one is that the protoplanetary disk, where the planets and the Earth form, was enriched with these heavier elements. So for that, you need a close-in massive a star that is there. So the star explodes as a supernova and enrich the protoplanetary disks with this heavier material, and now Earth can form. The problem with this is that the sun have to be just in the right position, so not far away from the supernova, so it can actually trap these heavier elements, but not so close, so it can destroy everything. So that has to be very fine-tuned. The second scenario is that has been by generations of different stellar populations, but you also need actually very high degree of fine-tuning, because you have to have the first generation of the stars that form, explode as supernova, so they have these heavier elements dissipating in the space. So they have a second generation of stars that catch this and then goes to different stellar stages, like the Wolf-Rayet stage, where the stars start dissipating these chips of material, and then you will have the sun or the protosun just in the right place, just in the right time to get this already enriched material and form Earth. So right now, that is a really open debate about how was the first stages of the solar system, but it seems that is not a surprise for us, that someone knows what it was doing, and he was all preparing all the details and all the scenario for us to come here. So yeah.
Thank you. Tim Williams from Seattle asks, what are some of the key differences between our solar system and other solar systems that we observe? And I'll ask my own second half of that. What are the features, some of the fine-tuning features that we see in our solar system that make life possible?
Mm-hmm. Yeah, well, as Dr. Ross have said in previous classes, our solar system is unique. We haven't found any other planetary system so far that is any close like our solar system. So basically this system that I show you, of course, are biased. So all these sources are massive and brighter protoplanetary disks. So these are very dense and big disks that we can observe at this level of detail, and they are also nearby because it's easier to observe. So for the planets that we have already discovered in planetary systems, usually what we found is that giant planets are really, really close to the star. I mean, and when I say close to the star, it's really close to the star. For example, the sun and the Earth is about 1 AU, and these giant planets can be even inward the orbit of Mercury. So it's really, really, really close. So that obviously rules out the possibility of a planet like Earth and planets that can have life on it. That is the main characteristics that we found. So giant planets really close to a star. Of course, there is the open question of whether is it because we don't have the capability yet to detect rocky planets, but that is also an open issue right now. But yeah, our solar system seems to be unique. We have these rocky planets inside, then Jupiter, which is the massive giant planet, and then the other giant planets. And one of the fine-tuning features actually for our solar system is that it have to come in a low mass density stellar cluster. So if you have a cluster that has too much stars, so the interaction with other passing stars and with these giant planets will rule out the possibility for life. So our own solar system and the evidence that we have for the solar system implies that the stellar cluster density have to be low. So that is also something that have to be explained in the models, but it's something that right now just seems to be really fine-tuned. You cannot have so many stars, but you cannot have so low density of stars in order to form planets.
Thank you. One of our technical people, Jamie, says that all of the and video for this, of course, is archived on paradoxes.org. One can go there and download this and watch it another 13 times, so we make sure we get all the content. It's wonderful.
Thank you.
Susan Lambeau says, ice needs to form on dust particles, doesn't it?
Yes.
That's
yes,
it?
Ice. Yeah. I mean, that's why dust is really important, because on the surface of this dust, if where molecules form, so if you are farther away enough from the star, from the radiation from the star, then these volatiles are going to be in the ice form. So they're gonna create a sheet around the dust. So that has a lot of different important features in protoplanetary disks. Because as you can imagine, an icy body is more easily to coagulate and to stick to other icy bodies, so they can form a greater or larger body. So that's why when you pass one of these condensation fronts or snow lines, where actually all the ice disappears and become gas, then these dust are not easily, it's going to be more difficult to stick material, because they don't have that viscosity that ice gave to the dust, and then produce these collisions and produce this small dust that are going to also have an impact on the emission that we see. So that is also a wide field right now, studying not only the dust and not only the gas like a global thing, but actually making very detailed models of the chemistry of these protoplanetary disks. So that is also a huge field. I'm not an expert on that, but it seems promising that we can have now the ability to even study the chemical part of these systems.
Thank you. Craig McMahon asks, JWST, assuming JWST ever gets launched, what are the particular questions about planetary formation that astronomers are hoping to answer?
Yeah, that's a very good question. A good thing about the JWST telescope is that it will observe.
Could you tell us what JWST stands for? Do you know?
Yeah, I mean, it's James Webb. Let me look at it like James WST, because I always forget. But it's the James Webb Space Telescope. So that will be just like the Hubble or Herschel, there's a satellite that will be launched, and it will observe in the wavelength range of, if I'm not mistaken, in the near infrared. So that is very important for us, because we can observe different processes with this telescope at a lot more detail than we have now. So we can actually see these inner parts of the disks that are emitting at this wavelength, so the surface of the disk, and we can have a better idea of actually the inner edge of the disks. So there's also a lot of effort in trying to understand this inner edge, where the disk starts to appear. So there's a lot of configurations that have been proposed, given different observations. Maybe these asymmetry things that we observe, like spiral arm or arcs, are actually because there's it's not coplanar, but it has some inclination. The inner part has an inclination over the outer part of the disk, and that is producing shadows. So these shadows can give the impression that you have spiral arms and that you have these moving shadows around the system that now we can also observe. So that's going to be critical in resolving this inner part of the disk, where actually grain growth is more efficient. So that's one part. And the other part is also going to give us the wavelength range to study very peculiar radiation that comes from the star, because of course, protoplanetary disk, the evolution of protoplanetary disk also depends on the environment. So if you have, you can imagine that if you have massive stars close to a protoplanetary disk, so this high radiation from the massive stars is going to impinge on these nearby disks. So you're going to photoevaporate the disks. So that have also been studied for decades now. It's called the proplets in the Orion Nebula cluster. So it's basically protoplanetary disks that are close to a very massive star, and this highly energetic radiation is dissipating the disk from the outside in. So what we have learned about this is that in these very violent conditions live less than other disks. So planet formation is not possible in these systems. So in the case of studying this type of processes of photoevaporating winds, the JWST is also going to be very useful, because now we know that stars doesn't form in isolation, but they form in these star clusters. And actually, one idea that is getting a lot of momentum right now is that photoevaporation actually between all the stars in the clusters plays a huge role in determining the evolution of the protoplanetary disk. So that's going to be critical for our knowledge.
Very good, thank you. Doug McComb again asks, what do you consider personally to be the most compelling evidence for the existence of God? Is it the fine-tuning argument, as many astronomers say?
Yes, for me, the most compelling evidence is the fact that the universe had a beginning. So what caused that beginning? And the fine-tuning, I mean, more and more that I learned about the universe and protoplanetary system like this, you can see that it's really hard, it's really difficult to form a solar system like our own solar system with this huge capability of having life in it that can live, that can drive. So yeah, for me, the most compelling evidence is the beginning of the universe and the fine-tuning that has to exist in order to have this amazing planet that we have.
Thank you. I want to say to everyone out there that I want to make sure everyone's questions get answered. And Norm Helgeson, I need to say, I read your question many times and I just can't, sorry, make sense of it. Could you restate it and send it back again, and I'll be happy to ask it. Stephen Posta in Texas asks, why are some smaller planet-sized objects absorbed by larger planets during the formation process, and other times they get made to be a moon to the larger planet? What causes the different outcomes?
Well, I guess, I mean, I'm not sure about those mechanisms really, but it can be the result of many different processes. I mean, in some cases, you have this giant planet that is massive enough so it can attract these other little planets. But sometimes if you have multiple configurations of planets, so multiple giant planets with rocky planets, it can produce these resonance regions where it can perturb the incoming body. So it depends really on the configurations. This really is a narrow range of configurations that you have several planets, so you have these parts of a disk that are not going to be stable, so that going to produce these planets to escape from the system. So actually, instead of just saying, oh yeah, this parameter is the key, it just can be the results of many different processes happening at once. I don't know if there's another part of the question that I missed at the end, maybe. I can't remember. You're mute again.
He says, what causes the different outcomes?
Mm-hmm. Oh yeah, so I don't know, I mean, it depends on the configuration of the system. Now there's a lot of exciting views of these new, really exotic objects that we call planets. So these are basically moons. You have the planet, you have the moon, and for some reason, there's some distortion or perturbation in the system, and this moon escapes from the gravitational potential of the planet and starts resolving the star. So before was a moon, and now it is a planet because it's moving around the star. So that's why we call it planets. So as you can see, there's a lot of interesting ideas that can happen, but it actually depends on the configuration that you have and the interactions between all of these planets and material in the disk.
Good, thank you. I want to tell everyone we're down to one question, so if you have a great question, get to it and I'll ask it. Norm Helgeson's asks, are there similarities in the unstable process thought to be involved in planet formation to those instabilities involved in star formation due to density variations in molecular clouds?
Well, actually, I'm not sure of that because I guess there can be similarities. I mean, there can be instabilities that can act in both cases, but I think the instabilities that are proposed, at least the ones that I talk here, to explain these superstructures are different from maybe the instabilities that you can find in stellar formation. And basically is because you have the disks and you have that the material in the disk, it's moving in Keplerian rotation, more or less. So that is something different between the global core scenario where stars form. So in this case, you have a disk that is moving a Keplerian rotation. And this instability is really that we called viscosity on the disk. The main reason, we don't quite sure, but the main reason of this is because gas is moving around. So I don't know if you know, but inner parts of these disks move quickly, move more quick than outer parts of the disk. So these inner regions move faster and these outer regions move slow. So as you can imagine, if you have a gas, they are moving at different velocities. So these adjacent regions of gas moving at different velocities will have this friction, and that will be reflected as a heating mechanisms. And that's what we call the viscous heating of the disks. So that's produced an instability that is what drives the material to go from the outer parts of the disk to the inner parts of the disk. And it's basically because the gas have this pressure gradient that is negative in the radial direction. And what it means is that the gas wants to go slower than the dust. So a small dust is coupled to the gas, so it moves just at this sub-Keplerian velocity, what we call sub-Keplerian velocity, because it's slower. But once you have bigger and bigger grains, these grains decouple from the gas, and now they want to move in Keplerian rotations, just as our planets. So the gas, what it produces is that slow down this grain because the dust want to go faster and the gas want to like break down the velocity of the large body, and that's what produced the migration of the material. So these instabilities are produced by different mechanisms, which is the rotation, the Keplerian rotation of the disk and the gas and the pressure gradient that is quite different of what is happened in these cores that are producing the stellar formation. So I don't really know if there are some instabilities that are the same, maybe in the sense of magnetic fields, but we don't really know much about magnetic fields, and that is a whole very study field that is very complicated. But yeah.
Thank you so much. Williams asks, have you had interactions with your colleagues about your faith in Christ, and what kinds of reactions have you experienced in these discussions?
Yeah. Well, yes, I have some interactions. I haven't had much of that, really, to be honest, because right now is where I'm starting to know this amazing work of reasons to believe and how to connect religion with science. And I'm very excited now and motivated to learn more and more about the scientific evidence in the case of a creator. But basically, and it was something that I didn't know when I enrolled in this career in science. In my naive view, I see the universe and I see that the world around us, and I was amazed by this beautiful designs, this beautiful creation. And when I enrolled in my PhD, I was really frustrated that I saw a lot of astronomers and scientists that actually doesn't believe in God. You know? So the reaction that I have in when I say that, yeah, I believe in God, is they say, well, I mean, I respect your position, but the main thing that I have heard is that say, yeah, I respect your position that you're a Christian, you believe in God, but once you get so I mean, you cannot tell me that the universe and the earth is John, because that's not what we observe. So I don't want to hear about it. So I think the job of reasons to believe into combining this evidence is actually very good. So people can actually see that the Bible teaches something that is very consistent with what we observe in the universe. So I guess just given this evidence can be of great help, hopefully, so people can actually see that science and religion are not in contradiction, but actually goes together. So
Great, thank you. Doug is asking a question that I think you answered at the beginning, but maybe it was before we officially started, so I'll just go ahead and ask it again.
okay, yeah.
Is there any way you could share your personal testimony of coming to Christ in a few minutes?
Yeah. Like as I said before, I've been a Christian my whole life. I mean, I grew up in a Christian family, so I have always believed in God and in Jesus Christ as my savior. So I don't have this interesting story of how you became to Christ, and I just been a Christian since I can remember. So that has been a very huge blessing in my life, because God has, been very good and has shown me always His grace and His love in my life. And now I'm very excited to use all my knowledge and all my expertise in astronomy, so I can declare His glory and talk about the message of of God, and how that is stronger the case for the Creator. So yeah, I've been a Christian since I was a little kid.
Thank you. Susan Lambeau asks a great question. She says, what telescopes do you observe from? How far from Valparaiso you are staying? And she says she lives in Valparaiso, Indiana, spelled the same way, named after Valparaiso, Chile. We are also a port city, she says.
Oh, nice. I didn't know you have also another Valparaiso, so that's good to know. Yeah, the main telescope that I use are actually in Chile. I have observed in the Las Campanas Observatory, so that has these twin telescopes, which is called the Magellan telescopes. So they are like 6 meters in diameter. So I have done most of the part of my PhD were on those observations, on those observatories, but I have the blessing of also working with ALMA data, so the one that I show you, and also with the BLT in Paranal. So that is North Chile. So I live in Valparaiso. So if you want to go there from Chile, you can go on plane. It's very fast. So it's just 1 hour, but I usually take a bus. So it goes, I think, for 7 hours. So it's not that long. I mean, before, during my PhD, I was living in Mexico. So that was long. I have to go all the way from Mexico to Chile and then to the observatory. And sometimes that same night you have to go and observe. So that was a lot more difficult. So I'm grateful that I'm now living in Chile, so close to these observatories.
Karina, I'm going to take the opportunity to ask you a question that I've always wondered about. Space is three-dimensional, and yet all the planetary systems form in roughly 2 dimensions. Is it not possible for a star or a set of asteroids to orbit a star at, say, a 90-degree angle to other objects?
Yeah, that's a great question. As I said on my talk, the natural outcome of planet formation, of stellar formation, sorry, that you have this core that is collapsing, is the formation of a disk. I mean, why this happened? Because when you are contracting material, so the size of the cloud is getting smaller and smaller, and is spinning. So if you want to conserve the angular momentum of this rotating cloud, once it gets smaller and smaller, so you have to spin up. So that produces a centrifugal force that is perpendicular to the rotation axis of the cloud. So that's why the collapse is not, I mean, is now concentrated in this direction and not in this direction because of the centrifugal force. So that's why you form a disks. So that was, you see that basically most of the planetary system that I show you is around these disks. Of course, you can have different interactions if you have massive giant planets, and actually there are a lot of objects that are not coplanar with the disk but at high inclinations. So now there's an open debate in what is the origin of these Kuiper belts objects in our own solar system, like Secna, which is a massive object that seems to be, well, actually resolved in a very elongated elliptical orbit in the solar system. So it's being proposed for that. To explain that, it has been proposed to be the result of a passing star, so interaction with an external star passing close to the sun, or with planet 9. So actually you can have these interactions with different bodies that are getting or passing close to the system and can perturb all these orbits. And actually there's a lot of ideas now that you can have a binary system. So imagine that you have these 2 stars and are orbiting like this, so in this direction. And now you have a protoplanetary disk that is perpendicular to that direction. So now we have been able to observe these systems more and more. And actually some papers suggest that actually this can be unstable state. So now we are start getting more and more data of these systems, that the binary system is like that, and now the disk revolves perpendicular. So yeah, that is possible actually, and you can observe it, and we observe it, yeah.
Thank you, now I know. Mel Peters asks, do all planets rotate counterclockwise or in the same direction, and why?
Yeah, so that is a very good question. All planets, I mean the main planets, not the dwarf planets, but the main planets, orbits have a prograde orbit. So they orbit the same as the sun revolves in their own axis. But you can also find different planetary system, exoplanetary system, that is not the case, that you have retrograde orbits of planets. And that is explained right now, as far as I'm aware, is because of interactions with passing stars, what we call a flyby. So a flyby is just a massive star, or a star that is passing close to these systems and perturb the orbit of these planets, and now it can produce these retrograde orbits of the planet, even in the system, or because the passing stars stole the planets in the first system, and then it got these retrograde orbits. So basically the main mechanisms to explain retro orbits have been the interaction with stellar passing stars. In the case of the solar system, see, we have these well-organized, if you wish, prograde orbits. It means that the solar system, the birth or the cluster where the solar system came from, have to be of low mass, so you don't have much interactions with the different stars around it. So that is why all the evidence implies that our solar system was born in a not that dense star cluster.
Thank you. Craig McMahon asks, as an observational astronomer, do your observations require an on-hands involvement at the observatory, or can you use the equipment remotely?
Yes. So there's different instruments, and they have different processes that you have to have. For example, the ones that I show you here, which are the main telescope, ALMA and Paranal, those basically are remote observations. So you put a proposal for the observations, and if you get accepted, they observe the sources that you want, given all the parameters or the things that you want to observe and when and how, and they observe it for you and then just give you the data. But a lot of other observatories are not like that. So you have to actually go to the observatory and be there all night or for a week or for whatever time you have to be observing, and just actually being there and do it directly with you. I mean, of course, most of the observatories have an operational astronomer, so that is actually the person that moves the telescope, and it's aware that everything goes well in the telescope. We astronomers, observer astronomers, actually don't move the telescope because, you know, we will break it for sure. So we just tell the operator, okay, now we can observe this source, go to these coordinates and observe this, observe that. But it depends on the observatory. The main telescopes usually have remote observations, but you can find a lot of different observatories that you have to go yourself.
Thank you. Doug's asking a question. He says it's from his wife. In our solar system, are some of the planets older than others? If so, what are the oldest and newest planets?
Yeah, that's a very good question. Not quite sure of the answer of that. What I have heard is that the first giant planet that was formed was Jupiter, and then it came the other giant planets. So I don't know. I mean, I know they have to be formed at different stages, at different ages, but I don't know how much different actually are between the formation of Jupiter, the formation of Saturn, and so on. So for what I know, giant planets have to be first because they are giant planets. So they have this gas content, and rocky planets are perfectly fine forming later on when probably most of the gas in the disk has been already dissipated. So I guess it's okay to think that rocky planets can be formed after the giant planets, but I don't know if that's always the case or not. So yeah, that's a very interesting question that I would check it out.
Well, we've got 2 minutes left, and we answered all the questions, which means now everyone knows everything. I'm wondering if Mark or Hugh, who signed on with us a little later, have any questions. If not, could you just make a couple of closing remarks and then maybe close us in prayer?
No questions from me. Thank you very much, Karina.
You're welcome. Thank you for inviting me.
Great talk, Karina. Glad I could join in after I finished my events in St. Louis.
Yeah.
Very good. Well, Karina, would you be comfortable closing us in prayer?
Yeah, sure. So let's pray. Thank you, Lord, for this day. Thank you for giving us the opportunity to learn a little bit more about the beautiful work that you have done, creating this amazing universe for us. Thank you for giving us the capabilities and the technology to go further and to observe more and more detail about this amazing universe that you have done for us. Thank you for filling us with your love and with your grace always, and help us to always be humble enough to accept your word and to always do your will. In Jesus' name, amen.
Karina, that was a marvelous presentation. Thank you so much for agreeing to be with us on the spur of the moment. And it's just really terrific. God bless you. And thank you so much.
No, thank you. Thank you for
Thanks,
inviting me,
Karina.
really.
Take care.
Thank you.
Bye-bye.
You too. Take care. Bye.
Bye-bye.